Alright, we're talking about sums. And so we were just talking about the index of summation where we stopped last time. And so now we want to talk about some properties of sums. And these are fairly obvious. We just need to really just write them down. So for example, suppose I have C times A1 plus C times A2 plus C times A3 plus C times AN. Well, you could factor the C out. And so the way to abbreviate this, right, is to say that the sum, I guess we're going to start with, I'll use the book's notation. Instead of starting with 1, we'll just start with an arbitrary n, m, CAM equals C. You can factor this, the thing out of the sum. Good. So this is property 1. You can factor out a constant. Property 2 is similar. If I have A1 plus B1 plus A2 plus B2 plus AN plus BN, we know that we can reorder the sum, right? And we could write this as A1 through AN plus B1 through BN, right? By the way, we could also do that as a subtraction problem, right? And so we could have a subtraction there. And so putting this in summation notation, I started with 1 again instead of m. I don't know why the book wants to start with m, but we'll go ahead and start with m for the book in our sigma notation. So this would be I equals m to n of a sub I plus or minus b sub I. And we've just shown that you could rewrite that. In fact, what this is called is distributing the sum. And so this is equal to the sum I equals m to n of a sub I plus or minus the sum from I equals 1 to m to n of b sub I. Good. All right. Finally, we want to see if we can find some formulas. For certain sums. By the way, we're doing this as kind of a build-up for chapter 5. So we'll see why we're doing this in we'll have to wait till chapter 5 to see why we're looking for these formulas. But something just like the, let's just say I'm summing I equals 1 to n of 1. What would that be? Well, if we write it out, that's 1 plus 1 plus 1 n times, right? So that would just be n. Good. So notice that if I summed I equals 1 to n of c, that would be c times the sum I equals 1 to n of 1, right, from our properties. And so that would be c times n. Very good. Let's see, I'm going to show that I want to try to show that the following formula holds. If I take the sum of the first n integers, 1 plus 2 plus 3 plus n, then I could write the sum that I would get will be n times n plus 1 divided by 2. I wonder why that is. By the way, just to double check this is true. Suppose I take 1 plus 2 plus 3 plus 4, well, let's do go up to 6 plus 5 plus 6. What I'm saying is that should be 6 times 7 divided by 2, which is 3 times 7. Is that actually 21? Let's see, that's 3, 7, so that's 10 plus 11 is 21. Very good. In fact, there's a little bit more clever way of writing this, because notice that if I, underneath this sum, if I had put 6 plus 5 plus 4 plus 3 plus 2 plus 1, and if I sum straight down, then notice that I get 7 plus 7 plus 7 plus 7 plus 7 plus 7. And so how many 7s do I have here? 1, 2, 3, 4, 5, 6. So that's going to be 6 times 7, and then this is twice too much, so I would divide by 2, and that's how you get this formula. So just to prove this in general, if I write 1 plus 2 plus 3 plus 4 plus n, I'm going to assume that that's equal to some unknown value s. And so I'd like to try to figure out what s is. Actually, we know what s is. We're going to prove that s is equal to n times n plus 1 over 2. Okay, underneath of this, I'm just going to go ahead and write the same sum here, but in reverse order. Let's see, maybe I'll, I guess 2 comes before 1. And then let's write in that this was the n minus 1 term here. Right, so that's also equal to s. I'm just writing the sum in reverse order. So when you sum straight down, we get that 2s is equal to n plus 1 plus n plus 1. Do you notice that? Plus n plus 1 plus n plus 1 plus n plus 1. And if we look to if we count how many we have here, we have n of them. Good. Therefore, this whole thing on the left just becomes n times n plus 1, and that's equal to 2s. And so that means that s is equal to n times n plus 1 over 2. Very good. This is a very famous formula, by the way. It's one that you really ought to know. Although since our test is going to be open book, I guess you don't have to memorize it, but know where you can find that formula. Good. All right. So I should say on page A37, oops, on page A37 there's a few more formulas. And you'll be using those formulas in the book. Use in the homework. Let's see, what problems was that? Were those 21 through 35? You can use them for problems 21 through 35 if you need to. So in these homework problems, some of the problems you can do on the calculator, and some you'll need to use the formulas for. Okay? Good. All right. Let's see, I'm going to set something up for next year, and that is the induction principle. It's a different way to prove a statement. So we want to prove a statement is true for all integers, or for all positive integers n. So it's very difficult to prove that a statement is true for all n, because you need to be able to show that it's true no matter what the n value is. So some people mistake that. They think, well, if I prove it true for like n equals 3, that's enough. Or if I prove it true for n equals 5. Okay, what we want to do instead is we want to use the induction principle to try to do that. And so the induction principle says that to prove such a thing, it's a two-step process. Two-step process to prove. To prove by induction. And this is a logical principle. My screen doesn't want to go up. Uh-oh. Let me pause. Okay, I'm not sure what that was about, but I think I got it. Okay. So the first step, let's go ahead and say 1. You want to show that the statement is true for whatever the starting index is, usually 1 for like n equals 1. Okay, now the second thing is something that people tend to get confused about, so let me say the whole thing first and then we'll see what happens. Okay, we assume the statement is true for, say, n, and then show that this implies the statement is true for n plus 1. Okay, and so these two things go together. So some people get confused. They say, well, if you're going to assume the statement is true for all n, aren't you all done? And the statement is no. We assume the statement, if the statement is true for n, then the statement must be true for n plus 1. So the two things kind of go together. Okay, that's a little bit hard to figure out here. So let's use a concrete example. And we'll just go ahead and prove the statement that we've already shown to be true. That is, the sum of the first n integers is n times n plus 1 divided by 2. Okay, so the induction steps would be 1. Prove true for n equals 1. And so on the left side we have 1, and on the right we have 1 times 2 divided by 2. The 2's cancel, so 1 is equal to 1, and the statement is true, 2. So we're going to assume that 1 plus 2 up to n is equal to n times n plus 1 over 2, and that this implies that the statement is true for n plus 1, which means 1 plus 2 plus 3 plus up to n plus n plus 1. Now if I plug in n plus 1 into my formula, I'll have n plus 1 times n plus 2 divided by 2. Okay, so this second statement is the thing I want to show that's true, but I want to use this thing to prove it. Okay, and so how am I going to do that? Well, we start off with the left hand side, 1 plus 2 plus 3 plus n plus 1. And notice that I've got the first n terms here. And I know from this formula that I'm assuming that it's true, so I'm assuming that this is equal to n over n plus 1, or n times n plus 1 over 2. Okay, and so now I'm on my way. Let's go ahead and combine the fractions. By the way, you might keep in mind what we're trying to show here. We're trying to keep in mind this. We're trying to show that. Actually, do you see it yet? Maybe not yet. Let's go ahead and multiply things out. N squared plus n plus 2n plus 4. Oops, that's an n plus 1, sorry. Oh, that changes my algebra, in fact. Because you see the common n plus 1 there, and then what's left over is n plus 2 over 2, and that is what we wanted. Very good. And so we have now shown, so let me state my conclusion. We know that 1 plus 2 plus 3 up to n is equal to n times n plus 1 over 2 is true for all positive integers n. Good. So that was our first proof, and I ran over a little bit, but I just wanted to finish off this induction argument. So again, I want you to think about what this means, just this piece, right? Whoops, I messed up there. Oh well, I'll bring you back in the next video and we'll get a better conclusion. See you then.